Hello again, this is Galen Pickett, Physics 151, Cal State University, Long Beach, and today I want to talk to you about internal energy and thermal energy with an example. So here's the example. I've got two masses. They're the same mass, so the number of kilograms for this object coming in is the same number of kilograms in this composite object. Now the composite object consists of this can with a plunger there and a spring inside. So with the plunger compressed, there'll be some energy stored in the spring, and there's this ratcheting mechanism so that the spring will not, once it's compressed, it won't expand again. So I got this mass is going to come inwards, and as soon as it hits this platform, it will start to compress the spring, but then the object is going to move forward, and eventually they'll both be moving together with the same final velocity. And the question is, what is the final, and how much is the energy that is stored in the spring in this process? So the director says, there's two ideas here, two things I don't know. I'm going to use the momentum principle that will tell me what the V final is. And I'll use the energy principle to figure out what is the energy that is inside the system, this internal energy of interaction, this spring energy. What do I know? The knowns. I know the mass of each object. I know what V0 is. And I know what the spring constant is. The unknowns, V final and U spring. The spring will be compressed by a distance L here in the final state. This whole thing is moving forward. It's not at rest. It's still sliding on a friction-free surface. So that U spring, I could equally well write it as 1/2 K times L squared. So I can, from the amount at which the spring is compressed, I can tell you what that energy is. So I've got two ideas, two unknowns, and I want to know both of them. So I'm going to have a well-formed solution here. For the momentum principle, I don't need to know any of the internal details here. I can write the first object as a dot moving with velocity v0. The second object is a dot at rest. That's the initial state. The final state is that they're stuck together, moving with v final. That's an inelastic collision. That's exactly what we mean by an inelastic collision. The change in the momentum of the system, again, let's say that the system is the two objects. The change in momentum of the system in the x direction is equal to the F net from the surroundings times delta t, but that's equal to 0 for one of these collision problems. So what we have is the initial momentum of the system, which is m0 plus m times 0, is equal to the final momentum of the system, which is equal to m times v final plus m times v final. I have two objects moving with the same velocity. And we've done this one many times. That's equation number 1. And now the energy principle. Again, but now we need this internal structure of the system. So the system is the two masses and the spring. Now the spring is a real spring. It's a real spring. It's got mass, so the M of the can plus plunger is the mass of the spring, the plunger, all that together. So if that's what the system, the energy of the system, there's three places where energy can go. The kinetic energy for the first object, the kinetic energy for the second object, and the interaction energy that's in the spring. The energy principle will say the change in the energy of the system is equal to the work from the surroundings, but the work from the surroundings in this case is 0. So I get K1 initial plus K2 initial plus U spring initial is equal to K1 final plus K2 final plus U spring final. Now let's put in what we know. The initial kinetic energy for object number 1, 1/2 m v0 squared plus 0, because the second object is at rest to begin with, plus 0, because the spring is unstretched to begin with, is equal to 1/2 m v1 squared plus 1/2 m, excuse me, that's a v final squared plus U spring final. And there is equation number 2 let me mark the unknowns in these equations so you can see exactly where they are. V final is an unknown, and U spring is an unknown. We have two equations and two unknowns, so we can solve that. So we'll go into execute now that I know that there's going to be a solution. Number 1 says immediately that V final is equal to M times V0 divided by M plus M, which is the same thing as V0 divided by 2. If that's what V final is, I can substitute that into equation number 2 and get 1/2 times M0 squared is equal to, there's two things which are the same here, so I'll write that as M times the final velocity is V0 divided by 2 quantity squared plus the potential energy that's in the spring in the final state. So I have 1/2 M V0 squared is equal to 1/4 M V0 squared plus U spring final. It means that U spring final is equal to I'll write it in a very strange way, 1/2 times 1/2 M V0 squared. So I've got my two answers now. Now we need to check them. For the skeptic review, the units of V final, here's my expression for V final. It's the same as the units for V0, so that is meters per second. No problem there. And my units for the energy that the spring has is 1/2 kilograms meters squared per second squared, which is joules. So the units work out, and there aren't any unknowns. The thing that I want to point out here is that in this case, the change of the kinetic energy was negative. The total kinetic energy in the system went down. Here is the initial system kinetic energy. Here is the final system kinetic energy. And the KE that went down wound up exactly in U spring. 1/2 of the original KE went into potential energy of the spring. And that's something that I really want you to keep track of when you're solving problems like this. It's a rule of thumb that you can always count on.